Hello everyone and welcome to Vetenskapsfestivalen, the International Science Festival of Gothenburg, and thank you all for joining our digital program tonight. Tonight's lecture is gonna address a question that I think we all have been wondering about, which is, are we alone in space? And to answer this question, we are happy to welcome Cynthia Sassenroth from the University of Pisa. Cynthia is a planetary scientist and she's working in polar regions of the Earth and Mars. And she will be addressing the question that I mentioned earlier, are we alone in space? Before I leave the floor to Cynthia, I would like to remind you that we have a chat where you can ask any question regarding Cynthia's lecture. And all of the questions will be answered at the end of the lecture. We'll address all of them at the end. And if you're watching from Hyperworld, please use Vimeo's chat so we can have all of the questions at the same place. That being said, I would like to thank you once more, and I leave the floor to Cynthia. Welcome, Cynthia.
Hello, everybody, and thanks, Emmeline, for introducing this lecture. I am a PhD student at the University of Pisa in Italy, and the last 3 years, actually, I dedicated my life to the question whether we are alone in space or not, by trying to figure out during which time and where Mars had water in its subsurface as well as on its surface. And astrobiology is actually, um, the science which tries to answer whether we are alone in space or not. Before getting into further details of what astrobiology is actually about, this is actually what astrobiology is not about, and we're also not speaking about these things today at this lecture. So science fiction won't be addressed, although it's very interesting to think about very highly developed alien species as well. We're not talking about conspiracy theories, of course, and also not about alien kitties, unfortunately, I have to say. Instead, at the beginning, I would like to give you a short overview about what astrobiology is actually about, what the subject is, and later we will dive into alien worlds within our solar system where astrobiologists and planetary scientists expect life to have formed in the past and where it might have or might still exist today. And later on, we will go further in the biology of organisms, how they actually can possibly adapt to the very harsh conditions which are prevailing on other planetary bodies and also moons. First, when you want to find alien life somewhere else, you need to very clearly define what life actually is. And this question can be really tricky because there are many different definitions elsewhere. NASA defines life as a self-sustaining chemical system which is capable of Darwinian evolution. This means that organisms have the potential to do metabolism, they have chemical reaction, they can reproduce, they can sense their environment, and also they can transform information from one generation to another. Another definition which is out there, it's from Vitsani, and it's a little bit more abstract. So it might apply also to life forms which aren't, which are common maybe elsewhere in the universe and which are maybe very, very different from life as we know it. He says that life is different from inanimated object by the capability of biocommunication. This means that organism has the capacity to sense, monitor, and also interpret information they gain from their surroundings. Also, there is organismic communication with the same species or with other species. And also, organisms or everything what is alive should have the capacity of intra-organismic communication. This means that cells can communicate with each other in the same body. It doesn't need to be a body, it also can be a cell. And this is called biocommunication. Um, and as when you really want to look for it, you will find very different definition of what life actually is. But in the beginning, you really need to define it so you know what you're actually looking for. Um, Now the question, how actually does alien life look like? What are we looking for when we go to other planets, other moons, and trying to figure out whether this system was inhabited or not? The maybe rather boring question is that we only can look for life as we know it. Otherwise, it's really hard to looking for something or trying to find something when you don't know what you're actually looking for. It's like going into a room and I'm searching for something, but you don't know for what. So you will find in the end everything and nothing. And life as we know it exists or is based on four building blocks of life, and these building blocks of life, every organism has in common. It needs nutrients to survive. It needs an energy source. It needs water. Water is extremely important for all the metabolic and chemical reaction in the cell or in the body, and also exists within the rather concept of time. So nothing's just there with a blip, but it's embedded within a certain time frame. And how do we actually follow the path of finding life elsewhere? Um, NASA says, or it has a pragmatism of following the water. So when a planet or a system has water, um, it's a main target to go there and look for actually for life. And within our solar system, Earth is actually not the only planet which has water on its surface or within the system itself. There are other planetary bodies which has this as well. Water is actually a very delicate element because it just exists in a zone which is at a certain distance from the star. In our case, it's the sun, and where water is actually stable on its surface. So when you're too close to the sun, water tends to evaporate, and then it's not available anymore for any organisms to use. And when you're too far away from the sun, the environment might be too cold, and water tends to freeze. Also, then water isn't available for any living organism. So you need an atmosphere and a planetary surface where water is stable on the surface. And a planet which is just right at the border is our neighboring planet, Mars. However, recent studies have shown that the surface of Mars is extremely dry and it's extremely cold, and therefore actually really, really hostile today. However, in the past, Mars was looking very differently. Um, because back then it was actually a very water-rich environment. By high resolution images which are available today, we can see a lot of geological evidence in the form of river streams, lakes, and even sometimes oceans on Mars, which are really strong evidence that liquid water was really widespread and very persistent during the ancient periods of Mars. Here on the left-hand side, you can see an CTX image of Varego Valles. You can see several streams which are very complex, and they have formed by very persistent and intense rain events on the Martian surface. So the atmosphere back then probably was way warmer and wetter than observed today. Also, another fluvial or like river system, which is quite common on the Martian surface, are so-called outflow channels. This is on the right-hand side, you can see an example of Casey Valles. It's actually the largest river system in our solar system and has the size of Europe. So it's several thousands of kilometers long, several kilometers deep, and hundreds of kilometers wide. And these forms or these channels actually haven't formed during precipitation or rain events, but rather by the spontaneous and chaotic release of groundwater. So somewhere in the hinterland, the surface destabilized and large amount of groundwater was actually released. And within a single or multiple single events, then these extremely large outflow channels has formed. Um, and of course, wherever you have rivers, also somewhere lakes are forming. Here on the left-hand side, you can see an example of two craters. One is in the very bottom left of the image, and then another one in the center right. And they are connected also with a small fluvial channel. And by careful geological interpretation, we know that several crater lakes have been filled once with water, which is then defined as a lake. And of course, wherever you have a lake, it's a way more stable system where water possibly existed for a longer period of time. And this is, of course, also interesting for astrobiology. And therefore, these lakes are actually a prime target of NASA, ESA, and other space agency to investigate further. So in the past, we had a lot of rover and lander missions which further investigated these sites. Here on the right-hand side, you can see an on-ground image of the Curiosity rover. And what you can see are these thinly laminated or bedded units or structures. And this is actually an outcrop of lake sediments. And here we can investigate the dynamics, the sedimentation rates, and also trying to figure out with other techniques what kind of chemistry in these systems have persisted during their formation. And then, of course, going into whether these systems also have been potentially favorable for life or not. Another quite prominent example of a crater lake is the Jezero crater and the Jezero delta. It is currently visited by the Perseverance rover. I think it was launched in 2020, if I'm right. But since a few years, we got some absolutely amazing images back. And deltas are actually a type of sediment which formed when a sediment-loaded river enters a standing body of water and then deposits. And deltas are really excellent because we can investigate how dynamic actually the river was, but also what kind of water conditions and environmental conditions have been present in the lake itself. Here on the right hand side, you can see a very nice outcrop where you can see different geological units. At the bottom, you can see this kind of cross bedding. This happens when a delta progrades, and on top, you can see it's so-called topset when a delta is rather stable or has a very low accumulation space. And by putting all these puzzles together, again, astrobiologists, but also planetary scientists can draw a very well picture of the environmental conditions at the site. And also with geochemical investigations, we then can figure out whether this was potentially a site for astrobiological life. Okay, now we know that Mars was in the past a very water-rich planet with lakes, with rivers, and potentially also oceans. But when we look at Mars today, it gives a very, very different picture because today Mars is classified as a polar desert with extremely limited water content on its surface and extremely low temperatures up to minus 170 degrees. So what happened? Actually, Mars just lost its entire atmosphere, so it's not capable anymore to contain large quantities of water in the atmosphere itself. and also on the surface. This is mainly caused by the smaller size of Mars. So Mars is just half the size of Earth, and it doesn't had or it couldn't contain a very long-lasting volcanism. So there was a lack later then of any magnetical field, and as Mars lost also its magnetical field, it was very sensitive to the solar winds, and these solar winds were actually carrying away the Martian atmosphere. This then reduced the atmospheric pressure and also the stability of water on its surface. So today, Mars is, as I said, a very dry and very cold environment. But is it really like this, or are there maybe any other signs or reservoirs where Mars might have still, or where Mars maybe still contains liquid, not liquid, just water? Um, the answer is yes. And not just Earth, but also Mars do have polar ice caps. And these polar ice caps are situated on the north and on the south pole of Mars. And on the right hand side, you can see that they are looking actually really interesting with these spiraling arms. This is a result of, of strong winds coming from the center of the ice cap in relation to the rotation of Mars, actually. And when you look also on the right hand side, you can see maybe already that the internal structure of these polar layer deposits is quite complex. And the water ice itself is containing out of water ice to a large majority, but also CO2 ice. In the past, there have been one space mission which was capable to actually investigate the subsurface of Mars by putting a radar on the satellite itself. And this is actually a cross section of the northern polar ice cap. Just maybe to give you an idea what you're looking at, the bottom, which is really grainy, this is the bedrock of Mars, and the uppermost layer where you can see these horizontal lines, this is the actual ice. The actual ice here is 1.5 kilometers thick, and the what is really striking by these results is that we have at the bottom a very reflective layer, and these might be related to liquid water on the bottom of these polar ice caps. Why is there liquid water at the bottom of the ice cap? Well, when you have an ice sheet, it induces pressure on the lowest lying units, and we also have a certain amount of salt in this area. And as well, when you induce pressure and increase the salt concentration, then the freezing point of water is actually lowered. So water just can't exist at over 0 degrees, but also can be liquid even below 0 degrees, up to minus 40 degrees, depending on the pressure which is induced and also the salt concentration and the type of salt. Then we have another very large water reservoir on Mars, which is called permafrost. Permafrost is not unique to Mars, but also exists very widespread on Earth. And permafrost is continuously or permanently frozen soil over several years. So it's not freezing during winter. And here on the left-hand side, you see an example of massive permafrost in Siberia. There's a human for scale. And also here you can see these layering, and there's some internal structure. On the right-hand side, you can see also an example of permafrost, but this is in Hellas Planitia. It's in the southern hemisphere of Mars. And what you can see on the top of the image, this is the top of a cliff. The blue part is actually a slope of the cliff, and then you can see in the lower part the bottom of the cliff. And the blue part is actually an image which shows that these sediments are very rich in water ice. Another, yeah, but just because you have water ice, it doesn't mean necessarily that this water is available for organisms. You need liquid water. So, are there maybe any geomorphological features which still host liquid water on the surface? And the answer is maybe. In the past few years, recurrent slope linears have gained a lot of attention because they are thought to be related to at least periodically or seasonal flow of water. These recurrent slope linears are these darker stripes which you can see on the slope, in this case a crater. And yeah, there's thought that they may have formed under the influence of water. The problem, however, is that when you have a, the problem, the open question is still where this water is coming from. So when it's coming right from the surface, we know liquid water isn't stable, and even if there's maybe melting of superficial permafrost, this source would be depleted at one point. So it's not a sustaining system. So there's the hypothesis that these water may be related to some groundwater reservoirs. All crater walls are usually heavily fractured. On the right-hand side, you can see a cross-section of a crater wall. So in the darker unit on the right, this is actually the crater basin. Then you have the terraced crater walls. And by an impact, you have the result that the bedrock is actually really shattered and they're creating faults. These faults are, in some instances, maybe connected to a groundwater reservoir. And as these faults represent an internal rock surface where water could maybe rise towards the surface and could be released on the surface periodically whenever the active permafrost soil might be weakened during spring and during summer. However, there's also the possibility that, or like many other voices say, that these recurrent slope lineae might be rather related to a dry process where no liquid water is involved, and this might be a relation or in relation to dust, which is just falling down the slopes and then creating these darker stripes. So in this, this is definitely certainly a matter of an ongoing discussion. Um, in general, Mars is an extremely hostile environment. So organisms on the Martian surface would have to deal with a lot of extremes. So Martian temperatures can change by tens of degrees in comparison to the night and during the day. Also, in general, Mars temperatures are extremely low. There's possibly no liquid water on the Martian surface. We have extremely high UV radiation. We have an enrichment in toxic salts in some instances, and also no oxygen. So currently, the Martian surface is extremely hostile to life as we know it. However, life might have found an ecological niche in the subsurface, and these features are called cryopecs. There are essentially entities of liquid water in otherwise frozen permafrost soil, which can stay liquid even at temperatures well below zero. Or maybe in other words, it's an extremely cold subsurface puddle. So these cryopecs form when water saturated sediments underwent a freezing trend, and they're usually also very enriched in salt, and also they are forming under increase of pressure, and these two variables actually lowering the freezing point of water in these cryopecs. On Earth, cryopecs also have been observed, and they can contain liquid water of up to minus 11 degrees. However, on Mars, where we also have an enrichment of other salts, these cryopecs might be stable also for longer geological time spans and even at temperatures below minus 11 degrees. And these cryo packs also, on Earth, they have measured to be stable over hundreds of thousands of years. And therefore, these cryo packs are certainly also on Mars a really interesting target for figuring out whether Mars have been favorable for life in the past, but maybe also still favorable for life today. Okay, this was Mars, but which is just at the border actually of our habitable zone. But are there actually also worlds beyond this zone which could harbor liquid water and therefore are suitable for life? The answer is yes, and the answer lies in the icy moons of our solar system. These icy moons are looking like this. The largest one are Ganymede and Europa, and most of them are moons of Jupiter and Saturn. One icy moon which was visited in the last few years was Enceladus. He is a moon of Saturn and was visited by the Cassis experiment. And actually, we found that Enceladus is not just an icy moon, but has a very complex internal structure. So the icy surface is actually several kilometers thick and is underlain by a subsurface ocean of liquid water. In the core of these icy moons, you often have a rocky core, and it was also evident that you have at the poles something which is called cryovolcanism. Cryovolcanism, cryovolcanism are icy plumes at the pole, and they're actually a result of repetitive planetary contraction by the tidal forces induced by Jupiter or Saturn. So when a moon is circling around the planet is extended and can also be pushed together. This causes friction and heat, and also can heat the water, and the water is then, as a result, ejected into space. And Cassini was able, so this was the space mission which was visiting Enceladus, was able to actually measure the chemical composition of these plumes, and it came out that these plumes had a large amount of liquid water as well as methane. Here on the image you can again see maybe a little bit more nicer cross section of the icy crust. Below you have a liquid ocean, and then you have the rocky core. Methane is actually also a byproduct of biological activity. However, it can be also formed by a chemical reaction between the mineral of olivine and water. And then you also have methane. And at the moment, it's still an ongoing discussion whether this methane is a product of life or whether this is maybe a product of a chemical reaction between the rock and the water. Okay, so now we visited some potential environments in our solar system which could potentially host life in the past, but maybe also host life today. And now you may think, okay, wow, this sounds extremely interesting, but this is so hostile. Does life even have a chance? Because it's so different from what we experience as normal. And there are some organisms which are actually also on Earth very well adapted to multiple extremes. By figuring out how organisms function in extreme environments on Earth, which are similar to those we find in the solar system, astrobiologists and planetary scientists can actually trying to understand what kind of mechanisms um, organisms here on Earth has created or are adapted to, so that they also maybe can survive elsewhere in our solar system. And the organisms which are adapted to multiple extremes are called polyextremophiles, polyextremophile microorganisms. And yeah, they are adapted to multiple extremes. For example, they can deal with extremely high or extremely low temperatures. They can deal with an increase in pressure. They can survive in a variety of pH environments, extremely high salinities. They're adapted to extremely high UV radiations and also the lack of oxygen. When organisms are exposed to these extremes, a lot of things actually can go wrong or it doesn't function as usual. For example, organisms have modified metabolic rates. Um, it can happen that proteins can be misfolded, that there are mistakes in transmitting the DNA, because also the DNA can be, of course, modified. And also you have, in many cases, you just have like cellular destruction. So this is a challenge which these microorganisms are actually facing. But we can actually go in certain habitats where there are microorganisms which are extremely well adapted to these extremes. And on Earth, astrobiologists go to certain places and looking for these organisms and trying to understand how they are adapted and how they survive in these extremes. Just a short overview. So, for example, sea ice and permafrost are an extremely good example for the modern Mars. But also, microorganisms or organisms have been found in the deep sea, in hydrothermal vents, in deserts, in the subsurface itself, and also in acid lakes. So it's actually a huge variety of environments where organisms can survive and also thrive. Um, Organisms which survive in extremely cold environments are called psychrophiles. This is a picture which was made by my colleague Ernst Tauber, and in the field here you can see my other colleague Jean-Pierre. He's also an astrobiologist, and this picture was made in the Antarctic dry valleys. The Antarctic dry valleys are actually the coldest and driest, one of the driest places on Earth. And you might think, okay, Jean-Pierre is the only living organism in this picture. Um, there are actually a lot of other organisms and species which are adapted to these extremely harsh and challenging conditions. One example are these lichens. They can actually deal with these extreme low temperatures and also with the extremely high UV radiation. Um, Prevalent in Antarctica. They have often higher degree of melatonin. So on the right hand side, you can see in the picture that these darker areas. This is a species of lichen as well. They have an increased melatonin content within their cells. So they're actually pretty well adapted to high UV radiations. Another survival mechanisms of other organisms, here in this case algae, are that they form layers in porous rock. They are called endolithophiles, so they're living actually in the rock itself. And there they're really well connected to larger changes in temperature, but as well also as UV radiation. So, and here they form like really nice communities. You also can see that you have a layer of algae, and then you have another layer of another type of organism, which also forms melatonin and is like closer to the rock. So they're where the exposure probably to UV radiation is a little bit higher. Then you also have halophiles. These are salt-resistant organisms. Also here, this is another picture which was taken in Antarctica. And here you can see a frozen lake, and the white um, ring you can see around the lake. This is actually salt. which was enriched there through constant evaporation. And a long time, scientists were sure this is like an absolute hostile environment, but also in these type of lakes, organisms have been found, and not just surviving but also thriving. Then you have thermofields. They're really well adapted to extremely high temperatures. Here in this case, it's a picture of Yellowstone National Park. But also thermofields can be found in the deep sea along hydrothermal vents, along with not just microorganisms, but these hydrothermal vents actually show a very diverse and complex community. Because also here you can find some crustaceans, also crabs and other more complex organisms, where scientists thought, which were just discovered like several decades ago. And next to these high temperatures, they're also really well adapted to the extreme high pressures, which are prevalent at these depths. Then you also have radiation-resistant organisms. This is a picture from an experiment on the ISS, where from my colleague Jean-Pierre, and here several types of organisms were exposed to the conditions in space. So this means a higher UV radiation, vacuum, heat was induced, cold was induced, and of course everything was taking place in zero gravity. And it was found that also under these extreme artificial conditions, also organisms not just survived, but also thrived in some instances. So, what are actually the boundaries of life? It's like when thinking from a human perspective, life is very limited to like a certain range of temperatures, of pressure, UV radiation, and salinities. But as much more we are understanding what life actually, or what kind of conditions life actually existing in, we're quickly figuring out that life is way broader, way more complex, and way better adapted to the extremes, not just on Earth, but potentially would be also adapted to multiple extremes, which the solar system is them exposing to. So coming back to the question whether we are alone in space or not, well, it's still an ongoing discussion. We're still looking for it. But in the last few decades, the field of astrobiology and as well the field of planetary science had made huge advantages of understanding the actual conditions of life, and also investigated several spaces, not just in our solar system, where life might have been existed in the past and in the future. And I'm sure that we will continue on this path, and coming to closer to an answer in the upcoming decades. This was my presentation. Thank you for your attention. Now I'm ready for your questions. Are you still on mute, I think?
True, I always do that. Thank you. I was saying thank you for this presentation, and we actually do have one question in the chat.
Mhm.
So the question is, are you excited by the colonization of Mars by Elon Musk because of the possibilities for new discoveries?
Um, well, ja, also, ja. I think I will believe it when I see it. So there's like still a lot to do, and of course, first we have to go to the moon, and it's like in the up. I don't know. He said like 2030 he will be there and colonizing Mars. When this colonization means that we actually can do better, more detailed science on the field, then I'm very, very excited about this, because this means that we can go to places which are currently mostly unavailable for rovers and landers, and we can try to understand the system Mars itself way better, and possibly also more cost efficient. But it's like cost efficient in space terms, so it's still expensive. But yeah, when the colonization of Mars means that we can understand this planet better and coming closer to the question whether Mars have been inhabited in the past and might be still inhabited today, then I'm very excited.
Great. Then let's hope that this can work. And we have another question. How likely do you think it is that life has existed elsewhere and died out?
Um, Very likely, in my opinion. When you just think, I think there's like this Drake equation, which considers all the possible of the amount of galaxies, the amount of stars, the amount of planets, and then it draws a probability of planets which might be Earth-like or suitable for life. There's like a number where this with worlds which could be inhabited, but also the question is, when do these life have existed? Do they exist at the same time as we do? And also have been this kind of worlds or like, I don't know, civilizations maybe possible to send a signal? Are we available to like receive it? But just like the sheer size of the universe, I'm pretty sure that there must be life somewhere. But where?
That's a
Yeah,
great question.
yeah.
Um, we seem to have many questions tonight, so let's go on to the third one. Which planet or moon do you consider have the highest potential to contain living organisms?
Which planet?
Or moon do you consider?
Ah, okay. I think Mars. Also just by the sheer amount of data we have, by liquid water on its surface, I'm going for Mars. But also like this is maybe also a bias because we know we also have these icy moons, and in comparison to Mars, we just have a very limited amount of data right now. So it could be that icy moons are actually way more favorable, but based on the evidence we have, it's Mars.
And last question for now. What do you think about the theory that life was brought to Earth with an asteroid?
Possible, yeah. It's like also the theory is called panspermia, and that yeah, the spores of life, so to say, have been transported from elsewhere where life might have been prevalent, and yeah, comets then transported or impacted Earth, and so to say, this was the onset of life. The other theory is that life originated on Earth, and this I think is the most common theory. But panspermia is certainly also definitely an option. Yes,
Could it be that it's the two theories that can complement each other? That it has starting developing on
be
Earth,
both.
but yeah.
Could be, yes, but there needs to be evidence. Yeah.
Well, I think that's all for the questions for tonight. I don't think we have any other, but I would like to thank you for participating in this digital program. It was really nice to have you here
Thank
with
you. Yeah.
us. And thank you to all of you who watched the digital program tonight. This was the last lecture of this year, and I hope that we can do that again next year. So far, I wish you all a very good evening.
Thank you. Thanks for having me.